And welcome to this video. I'd like to thank y'all for stopping by and joining me. Of course, I appreciate y'all's support. In today's video, I wanted to really talk about exponential functions, as they have some very useful properties for modeling change. I will be using James Stewarts' calculus early transcendentals for purposes of teaching this video. However, I have paraphrased most of these definitions and also added my own twists and problems into this. So I want to start out, how is x squared and 2 to the power of x different? Well, they both have the same amount of variables and constants, however, they are very different. To start out, let's look at x squared. X squared, well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and then 10 squared is, of course, 100. Now, if you look at 2 to the power of x and start inputting x's, you'd see that 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. 2 to the power of 6, 64. And this goes on 128, 256, 512, and then 1024. And you see that in the end, whereas this x squared looked to grow faster, by the point of x is equal to 4, 2 to the power of x was growing faster. And actually started growing faster at a much quicker rate. Now, let's propose this question. What is exactly an exponential function? Well, an exponential function is any function that takes the form of y is equal to f of x, which is equal to a base, which is a constant, to a power of a variable. So this x could be a t, it could be a q, I don't really know. It can be any variable. And of course, we can also apply any manner of stretches or shifts or reflections with our already existing rules. For example, if we want, we can do y is equal to 5 times by negative x plus 3 to shift the graph up 3 units and also rotate it about the y-axis. A more generalized form of an exponential function, especially if you're working with something like population or interest in a bank account, you might see y is equal to p, where p is initial value, a to the x. But, yeah, there we go. Continuing on, let's see how we can, I already went over this, so I won't worry about the algebra part. How do these graphs look? Well, I have a generic looking function here, and I want to give 3 cases, and I'm going to do it in 3 different colors. So on white, I'm going to say b is greater than 0, b is equal to, I want to do blue, and then b is equal to 0, and finally b, I messed up, I'm sorry, I want less is greater than 1, is equal to 1, and is less than 1. But for this one, I'm going to just add the restraint that it also needs to be greater than 0. So what is this graph going to look like? Well, let's start with the greater than 0. Well, no matter the exponential function, as long as it's not been stretched or shifted, it should always pass through the point 0, 1. So its graph will look like a rocket taking off. And it's going to start small and end incredibly large. Going to, if it's equal to 1, well, 1 to, no matter what power you raise it to, should be equal to 1. So, yeah, it's just 1 throughout. Now looking if it's less than 1, interestingly enough, we see it as though it's like a shift. But rather than it get really big, it's going to get really small really quickly. Now that's an interesting thing about the exponential function, is that we really have two ways of mirroring it around the x-axis or the y-axis. We can either raise it to a negative x, y is equal to a to the negative x, or a can be less than 0, or less than 1. Continuing on, I wanted to come over here, and if you want, you can try to graph these on your own. But, and I'll give you a moment to maybe sketch that on a piece of paper. But I'm going to, once again, I'll use white for the first, blue for the second, and orange for the third. So, or actually I'll use pink because I used white to color in the graph. Okay, so let's start with y is equal to 2 to the power of x. Well, it's going to be really small going out, and then it's going to go really big. I did not want my thing to do that. Well, I suppose I have to... Oh wait, I can undo it. Remove that from existence. Would not be a video without the camera randomly appearing. So I'm going to just plot a point. So 1, 0, 1 is going to be my first point. Not now. Fine, I'll just do like a horizontal dash. 1, 2 is going to be my second point, and then 2, 4 is going to be my third point. So this graph is going to look something on the lines of this. Sorry for being a little squiggly. Okay, now if I was to graph the same thing, you'll notice that as the powers of x are further negative, the higher the constant value, the smaller it will be in quadrant 2. So it's going to go up, and it's going to go up, and it's going to go up, but in quadrant 1, it's going to increase faster. Now, if I have y is equal to 1/2 the power of x, it's going to look something on the lines of this. In fact, it'll be less than it. Now, why might this be the case where if this value, or let's go back to pink, where if b is less than 1 but greater than 0, why does it still reflect the graph over the x-axis? Well, in most cases, when you raise an integer to a negative power, let's say -2, what this really does is it's going to take the reciprocal and square it. So that would really just be 1/4. So really, this graph up here is 2 to the power of -x. And a more generalized form, and of course this thing is opened up again, have to get rid of it, of this is negative, or 1 over a to the power of x is equal to a to the -x. And this is just one of our properties of exponents. Let's work with some rules for exponentials. So if we ever have a constant b raised to x plus a y power, it can be divided up by doing b to the power of x times by b to the power of y. Similarly, if you have b to the x minus y, you can you can break it up by doing b to the power of x divided by b to the power of y. If you ever have a power raised to a power, the way that you can resolve that is you're going to multiply the powers together. And whenever you want to, or you have two constants a, b, raised to the power x, you can distribute the x, only if you're multiplying it. And in which case you'd get a to the x times by b to the x. So I actually have gone through and wrote out some rewrite and simplify each expression for you. So let's start out with this first one. And I actually want to maybe make this a bit simpler on this. So we're going to rewrite this as 2 to the power of 2 raised to the third over 2 to the power of 4 to the fourth. And what this allows us to do is we can use some of our properties. We get 2 to the 6th over 2 to the 16th. And we can now make this 2 to the negative 10th as our simplified form. Now this one, we can use our algebra skills once again, and we really only have to cancel this, and we would get an a cubed times by b to the fourth. Continuing onward, now we will have 7 squared times by 4 squared over 7 cubed. So in reality, what this will look like is 4 squared over 7. Now I'll give you a moment to try these last three. Maybe pause the video, and then I'll work them. Alright, let's get started. So we have pi to the 9th, as we're going to distribute u and multiply, so it's going to be 9. And then we also have 3 to the, or e to the power of 24. This is just a basic addition, so this is really going to be, so this is really just 5 times 5 times 5 times 5 times 5 times 5. So you can just see we can add the exponents, so it's going to be 5 to the 7th. Nope, did I have 3? Yep, that's right. Now this one is, I think, going to be the most challenging one for the exponential properties. So to start out, let's call this top part bx plus y all over bx squared. That's raised to the x. So I can distribute that, so we'd get bx squared plus xy all over bx squared. So what this will do is I can subtract this, so we get bx squared plus 2xy minus x squared. So we really just get b, I don't know where the 2 came from. There we go, bxy. There we go. Let's look at the number e. So e comes up whenever you're looking at the continuous rate of change of like a function. Interestingly enough, though, it is derived whenever you take a limit. So later on, I'm going to prove to you that the value of e using limits in the next chapter and show you how you can derive that for yourself. But I guess the last very important thing that you really want to know is how to convert one base to another. So the way that we can do this is, let's say we have a base. Let's say we're going to work with y is equal to 1,000 times by 7.5 to the t. Now, this value we might not want to work with for a variety of reasons. More directly, it's not as easy to work with as our letter e. So we're going to convert this. Now, the principle is going to stay the same. So we're going to set the equations equal to each other. So we're going to say that 1,000 e to the kt is going to be equal to 7.5 to the t. Now, a way that we can solve this is to divide everything with t's to one side. Or wait, this needs to have 1,000 on it. 1,000, 7.5 to the t. So the thousands will cancel, but we're still left in a to the kt is equal to 7.5 to the t. Now we're going to use logarithms, which we'll talk about later, to bring out these exponents out in front. So we'd get the natural log of 7.5 to the t. And this would look like kt, and the natural logarithm will actually cancel the e. So we would get the natural log of 7.5 t. Now we just have to get the t's to one side. So I'm going to subtract the natural logarithm over, or actually, scratch that. So normally whenever we're doing base conversions, and I actually forgot to mention this, you normally can not worry about the t value because they're the exact same on both sides no matter what. So the t's will also cancel each other, although it won't look like that. So you would get k is equal to this natural logarithm of 7.5, and now we can rewrite the equation as y is equal to 1,000 e to the natural log of 7.5 times by t. So, and that is the basic on how to rewrite n to another base. Now let's do a few practice problems. Well, let's see. Let's find the exponential function. Find the exponential function such that it has points p of 1, or 2, 7, and another point 4, 19. So the way that we are going to do this is we know we have a basic function y is equal to a to the, and we're just going to call this base e for the purposes of this, And let's actually change that to be a constant. E to the kt. So let's see, how are we going to do this? So we're going to plug in 2 points, and solve for missing variables. More specifically, we want to solve for k and c and k. So the first equation we're going to get is 7 is equal to c e to the 2k. And we're also going to get the equation 19 is equal to c times e to the 4k. Now the way that we're going to solve this equation is we're going to get the c's by itself, and we're going to plug in the c's. And then we're going to take that resultant and plug it in for k. So let's see. We are going to call c in this top equation. C is going to be equal to 7e to the negative 2k. Now we're going to plug this in down here, and we get 19 is equal to 7e to the negative 2k times by e to the 4k. And now what we can do is we can add the exponents, because they're both exponential. So we'd get 7e to the 2k is equal to 19. Divide the 7 over, and we get 19/7 is equal to e to the 2k. Now we just need to take the natural log of 19 over 7, and then is equal to 2k. And then k is going to be equal to the natural log of 19 over 7 over 2. Now what we can do is we can plug this value of k into the equation and solve for c. So we are going to, and let's actually just plug that into our calculator. And after plugging into our calculator, we get a value that is approximately 0.4992. Which I'm just going to say is 0.499. Now that we got that, let's solve for c. And we already have a convenient expression we are going to use. So c is going to be equal to 7e to the negative 2.499 times by, 0.499. And plugging that expression into our calculator, we should get c is equal to 2.57894. So our final equation would be y is equal to 2.579, I'm going to call it, times by e to the negative 2 times by 0.499t. And that, my friends, is the equation for our line with such a point. Of course, you can clean up that exponent a bit, but I'm not going to here. Let's erase and do another problem. Delete. Okay. And then delete that as well. Alright. The next problem I want to do revolves around our difference quotient, since we haven't talked about that in a while. So if f of x is equal to 5 to the power of x, show that Or let's make this 4 to the power of x. Show that f of x plus h minus f of x over h. Or not show that, but find. So this is actually a really challenging problem to work, and it's going to require a lot of exponential tools. So we get 4 to the power of x plus h minus 4 to the power of x all over h. So how do we work this? Now normally I say we are done whenever it cancels, but I don't think it will cancel in this case, or so we will learn. So what we're going to do is we are going to call this numerator 4 to the power of x times by 4 to the power of h minus 4 to the power of x all over h. Now looking at this, I think there's one way we can simplify this, and we can leave all of the h's inside. So what this is going to look like is it's going to be 4 to the power of x times by 4 to the power of h minus 4, or minus 1 actually, all over h. And we are done with that. In general, I think after this, you will be very well prepared. I want to thank you all for stopping by and listening. I hope you all have a wonderful rest of your day and have enjoyed. Have a great rest of your day. Bye-bye.